Okay, in this video I'm going to talk about the arithmetic partial derivative. So recall that the arithmetic derivative is a function d from natural numbers to natural numbers defined by the two properties. So first is that for any prime number p, we have d of p is equal to 1, so it's equal to 1 for all prime numbers, and second is the product rule. So for any two natural numbers m and n, we have d of m multiplied by n is equal to d of m multiplied by n plus m multiplied by d of n. So the similar to what we have for the regular derivative of functions in mathematical analysis. So basically now the idea is to introduce the function dp, like with p is the index here. So this would be a partial derivative with respect to the prime number p. So let's write this. So let's fix some prime number p. Prime number p, and so the partial derivative would be with respect to this prime number p. So this is the parameter that we fix in advance. So now we define a function d with index p from natural number to natural number, and another notation would be like a regular partial derivative, like in mathematical analysis. Like it's d and the notation for the arithmetic derivative is also d over no, I don't think there is a notation here. The notation here is like with the prime. So d of n is also denoted sometimes as n prime, like this. And and for the partial derivative it's like this. So yeah, so this function partial derivative is defined by two properties. So first, for this prime number p that we fixed, it's equal to 1. d of p is equal to 1 for all other prime numbers, for any prime number q, let's say q that is not equal to p, right? So d of q is equal to 0. So basically for all prime numbers it's equal to 0 except this one special prime number for which it's equal to 1. And the second, the product rule is exactly the same. So this, let's write this. For any two natural numbers, we have dp of m multiplied by n, dp of m multiplied by n plus m multiplied by dp of n. Yeah. So basically the product rule we keep the same, and instead of saying that it's equal to 1 for all prime numbers, we say that it's equal to 1 only for one specific prime number, and for all other prime numbers it's equal to 0. So this is a partial derivative. So yeah, just about this notation, so just to explain it fully. So this notation, it means that d of p of number n is denoted sometimes as dn divided by dp. So that's what I meant by this notation. Okay, so let's derive the formula for the partial derivative. So recall that for the full arithmetic derivative, there is an explicit formula. So if the number n is is expressed as the product of prime numbers, so it's basically the sum of pi by I, where I could be repeated, then d of n is equal to n multiplied by the sum of 1 over pi. Again, remember that pi could be repeated. So if n is divided by n is divisible by pi squared. So if the pi is if some prime number is occurs as a square in the oh my god, sorry, it's not the sum, of course, but the product here. Yeah. So if some prime number occurs twice here, so it's divisible by p squared, then here in this sum it would also occur twice, this prime number. So another way to write this is if we have different prime numbers pi, but with the powers ni. So like this, from this we write that Pn is equal to n multiplied by the sum of ni over pi. Yeah, so this formula is kind of more beautiful for the full arithmetic derivative, but for the partial we would need to use this one. This is more convenient. So for the partial derivative, basically the formula is similar, except that we need to put to zero all p that are not all pi that are not p. So basically the partial derivative of n, so if we have n like this, so then the partial derivative is equal to n multiplied by the sum I and I over pi, but the only I, only when, so only not the sum by for all I, but only for such that pi is equal to p. So basically we have only one term in this sum. So in other words, this is equal to either so let's say that, so if there exists such pi that pi is equal to p, then the sum would be equal to n multiplied by ni over pi for this specific index I, and otherwise it's just zero otherwise. Yeah, so in other words, like let's rewrite it another way. And for now, like I'm just giving this formula like without proof, but we will need to verify it. We will need to prove that this formula holds. So in other words, so if n is if n is not divisible by p, so if n is not divisible by p, then the partial derivative is just 0. If n is divisible by p and it is equal to p in some power raised to the power k, let's say, and k would be like this ni basically, multiplied by the rest. So let's denote the rest by I don't know, like q. So if n is expressed this way, such that also q is not divisible by p, right? So then, so like we accumulated here like all divisors, like all prime divisors that are equal to p. So all power, like the power of p that n is divisible by, it's exactly k. So then the partial derivative of n is equal to n multiplied by k over p. Yeah. So so to prove this formula, like and it's easy to see that like this what I wrote, like basically this formula is exactly equivalent to this. So these two formulas are just exactly the same, just different way to write it. So to prove this, first we observe that the partial derivative is like this function dp is defined fully by these two properties, right? Because like when we have a number, like it can be represented, so either it is prime. So when we have a so let's say we have a number n, right? So we have some number n. So either it is prime. So either n is prime, in which case like the dp of n is defined. Or it can be expressed as a product of two smaller numbers, right? So it's the product of let's say n1 and n2, right? Neither of which is 1. So both such that both n1 and n2 are natural, of course. N is also natural here. And n1 is strictly less than, so strictly yeah, from 2 to n1 to n minus 1. So it's strictly less than n, and n2 is also from 2 to n minus 1. Yeah, so in which case we use the so in this case we use the product rule. So we write that dp of n is equal to dp of n1 and 2, which is equal to, like, well, let's write it like dp of n1 multiplied by n2 plus n1 multiplied by dp of n2. And so we basically this is a recurrent relation. So we reduced the definition of this to the definition of dp for smaller numbers. So then for each of them for n2 for n1 and n2 we again apply the same argument. So either it is prime or it is expressed as a product of two smaller numbers. And so continuing like this, we eventually would arrive at a number. So like this, all of this proves that the partial derivative is defined fully by these two properties. So and this is the similar argument, by the way, to the full arithmetic derivative. Yeah. So but it doesn't yet follow from this that it is a correct definition. So it might be that if we choose different products here, right? So like n1 and 2, and it's also, let's say, equal to n3 multiplied by n4, right? Like this expression is not unique. Then expanding it like this, similar using the other numbers n3 and n4 instead of n1 and n2, like it might be that we would eventually arrive at a different result, right? So like the correctness of definition is not yet established. So all we proved for now is that this function, these two properties, the values for prime numbers and the product rule, they fully define the function dp, the partial arithmetic derivative. So now what we will do is we take this definition. So we take this basically as a definition, and we prove that then it satisfies both of these properties, right? So if we prove that, then it would follow that it defines the same function. So, and since this is defined correctly, so then this would prove the correctness of the definition and also the full formula. So let's so what we'll do, so let's define this as a function d prime. So it potentially could be a different function. So dp prime defined like this, and we will prove that it satisfies both of these properties, and from this it would follow that dp prime is equal to dp. So this would prove everything. So since we have that, so the first property, so the first property that for prime numbers is kind of trivial, right? So for prime numbers, so dp prime of p, so by this expression, so p is expressed as p to the power of 1 multiplied by 1, right? So so this would be equal to p multiplied by k, in this case would be 1 over p. So I wrote this formula, right, for this case, which is equal to 1. So this is exactly what we need. So I wrote d of p, not d but dp, d with index p, and here as well. Yeah, I'm sorry, it should be d with index p. Okay, so, and for any other prime number, for any prime p, for any prime q that is not equal to p, so what we have is dp prime of q. So again, if it's not divisible, then it's just 0. Or we can actually even skip this special case, because this case captures it as well. Because if k is equal to 0, right? So yeah, so we can skip this special case, because if k is equal to 0, so if k is equal to 0, then we have dp prime of n is equal to 0, because k is then 0. So n is not divisible by p is exactly correspond to the case of k equal to 0. So so this formula captures this as well. So in this case, q is not equal to p, so q is not divisible by p, so this would be 0. So this exactly satisfies this property. So now the product rule. We need to verify the product rule. So for any natural numbers m and n, we have so let's say that m is equal to p to the power k multiplied by q, and n is equal to, well, where q is not divisible by p, right? And n is equal to p to the power l multiplied by r, where r is not divisible by p. So if we have these two representations, so then the product, so dp prime of the product mn is equal to dp, so we need to verify if this is equal to dp prime of m multiplied by n plus dp plus m multiplied by dp prime of n. And so we have so the left hand side is expressed as d okay, so it's dp prime of p to the power k plus l, multiplied by q multiplied by r, right? So this is the expression that this is this expression basically, for which we have the definition, and so this is equal to then mn multiplied by k plus l over over p. And so this is equal to m multiplied by k over p. This is equal to n multiplied by L over P, and so the whole right hand side is equal to, so m multiplied by n, and here m multiplied by n, so mn is a common multiplier, common divisor, so we write that this is equal to m multiplied by n, or like okay, let's write more carefully. Just let's write the full expression. So m multiplied by k over p multiplied by n plus m multiplied by n multiplied by l over p, right? So this is equal to mn k over p plus l over p, right? And this is equal to mn k plus l over p. So we look here and we look here. This is exactly the same expression. So indeed the left hand side is equal to the right hand side. So this equality holds, and the question mark is, we can remove the question mark. Yeah, so this proves that the product rule holds for this function dp prime. So both the first property and the second property holds. So since they both hold, and since, as I explained before, these two properties fully define the function, it follows that dp prime is the same as dp. So dp prime defined by this formula is the same as dp. So it follows that dp prime is the same as dp, is the same function. And so then from this it follows the formula for the, so if n is expressed as p to the power k multiplied by q, where q is not divisible by p, then dp of n is equal to n over k, n multiplied by k over p. So, and now we also observe that the full derivative, the full arithmetic derivative d of n can be expressed as the sum of dp of n for all prime number. So p such that p is prime. So like it's kind of the infinite sum, but for remember that when n is not divisible by p, like it's just 0. So like technically it's an infinite sum, but for prime numbers larger than n itself, like it would be always 0. Yeah, so it's kind of curious that the full derivative is equal to the sum of all derivatives, and like the proof is basically from the formula. So okay, so yeah, so we have this formula, and so to prove this formula, we basically recall that the like we take the formula for both of them, the formula for the full arithmetic derivative and for the partial arithmetic derivative. So for the partial arithmetic derivative, yeah, so we take this formula, and for the full arithmetic derivative we take this formula. So this is the explicit formula, and we notice that under this sum, like each term of this sum, so basically this multiplied by n, so this would be the partial derivative. So notice that n multiplied by ni over pi, this is simply the partial derivative of by the prime number pi of the original number n, right? So then this whole sum can be written as the sum by I of dpi of n, and this is simply now the sum of dp of n for all prime number p, so when p is prime. And this is because we can add the prime numbers that n is not divisible by, because the partial derivative is 0. So basically this sum differs from this sum only by 0 terms. So when we add all other prime numbers to the sum, we simply add the zero terms. So basically this sum that is equal to d of n, this is exactly the formula that I've shown here. This is exactly the formula. Yeah, and another way also to look at this is that the partial derivatives are kind of a basis of all functions for like with the second property, with the property that the product rule holds. So basically, like if you consider an arbitrary function for which the product rule holds, but we don't know its values on the prime number. So the first property we drop, we keep only the second property. Then for all such functions, like they are not obviously fully defined, but for all such functions, like the partial derivatives look like a basis of all such functions, because they are kind of like each partial derivative is equal to 1 for one specific prime number and 0 for all other prime numbers. And the full arithmetic derivative, which is also like for which also the product rule holds, but it's defined differently on the prime number. So it is expressed as a sum of all partial derivatives. So it is kind of a linear combination of this basis, kind of a basis. Like so, like it would be interesting to prove like the statement that any such function that satisfies the product rule can be expressed as a linear combination of the partial derivatives. So like I'm not going to prove it here, but like I'm just saying that it would be an interesting statement. But the partial derivatives, they do look like a basis, because like they defined as 1 for one prime number and 0 on all other prime numbers. So Yeah, and so for the full derivative, the linear combination is simply the sum. So the sum of all partial derivatives. And for other, like if we define differently on different values on the prime numbers, we would get potentially we would get a different linear combination. So basically that's it for this video.